Hey class, so now that we've worked our way down from considering how to simplify geometry and discard whole regions all the way down to using the view volume to do that, bounding volumes, that kind of thing, and clip space and rasterization, I want to go back out the other direction. So I want to go back to this question I had at the beginning of how we can just discard or not even consider whole regions of our world. So I'm going to talk a little bit about scene or world level data structures. Okay, so we want to be able to organize our data or sort our geometry somehow. Into a data structure that will enable us to basically ignore whole regions, right? That enables us to quickly, that's a key there, discard large regions of geometry. Okay? So we want to make it so that if we have our world set up, once I know where my camera is, if I know something, everything else is behind me, I don't even need to consider it. I just don't even touch it. I skip the list. And an example I think this relates to is binary search, right? So in linear search, remember linear search is where we just, if I have 1,000 items, I check each one for what I'm looking for. In linear search, I do one check, and if it doesn't work, I discard one item, right? So this is big O of n. If I have n items, it takes n checks. However, in binary search, right, if my data is sorted appropriately, then with one check, I get to discard half my data. Half my data goes away. So one check half again. And so this is actually, big O of log, actually base 2 of n, doesn't really matter. A big O log of n, so it's way faster. So this is awesome. If we have our data sorted, we can do binary search. Can I sort my geometry in a way that lets me do similar kinds of queries? So can we do similar approaches to 3D geometry? Yeah, we can. And there's actually a lot of approaches to this, and there's a whole bunch of them. I'm going to go over 2 examples because once you understand the concepts, I think all the variants out there are just different versions of the same kind of thing. So the goal of this section, so in this, yeah, we got it. In this section, I'm only going to briefly go over these ideas, okay? We only briefly cover the concepts. If you need more information, you kind of just need to get a reference. So use a reference. There's so much good code online. These are old ideas. There's pseudocode, there's code out there, there's tutorials. So just check online if you need more information. The goal here is just to get you to understand the basic ideas behind these. Now the first one I want to talk about is called binary space partitioning. And this is a really neat idea. And it sounds like a binary search tree because it kind of is. The difference is you don't have a midpoint of data like you would have in an array for binary search. We have this open 3D world. So let's learn a little bit about how that would work. So the idea is that I'm generating a tree. Okay, and I'm making a tree which divides and divides and divides. And at each note, I divide the scene into two. Each node, sorry. To two. If it's 3D space, I'm using a plane, right? If it's 2D space, I'm using a line to divide my space. Now I'm going to illustrate this, but I'm just going to do it using lines. But you can imagine these are they're planes in 3D, okay? Okay. I'm going to, yeah, sure. I can number these later. All right. Maybe I'll just do it now. I'm going to call this object number 1, object number 2, object number 3, object number 4. I'm going to erase this one for now. Object number 5 and 6. Okay, so what we want to first do is, 1, we choose a plane to split the space. Okay, so we choose a plane to split the space. Now the key here is, unfortunately, this takes time. If it's, or you can do arbitrary. So you can just say, pick an object, let's split the world based on this object. But then you might not get the most efficient. So if you want an efficient plane, you try to find a plane that splits the geometry in half very nicely. And that takes a lot of time. So it's not something you do live, you do it offline, okay? And then also, as we've learned, planes have a front and a back. So we pick a front. And now we start building our tree, okay? And then, so A down here now has a front and a back, okay? And we can store things on either side of that. Now, as an aside, if any objects are now intersecting our plane, are basically split, then we have to split the object into two and put one on either side of the plane. Okay, so again, it's slow. And the reason for this is that in this example here, it's really easy to see. I can just pick a line that doesn't intersect anything. But in 3D, in a busy scene, you're inevitably going to get, that's your best line, crud, we intersected this thing here. So you don't need to split it. On this side, I make a triangle. Oh, I want to keep triangles. On this side, I make 2 triangles. So whenever you get an object that you've cut, you test, when you make a plane, you test all the objects that are not accounted for. Oh, I split this one. You split into 2 and you make more polygons. You make more triangles, okay? So you split into 2, or in this case, or more polygons. We're using triangles, okay? So that's it. And then 2, we recurse until only one object in each zone. In each remaining zone. Okay, so I'll do the front first. So I'll call this A, right? In front of A, we have, well, maybe we'll split here. And I'll call this B. So B, now in front of B, we have, 1 and 2, so we need another plane called C. Okay, so we have C. In front of C is 1, behind C is 2, in front of B is C, behind B is object 3. You can see that there. Behind B is object 3. and then now we do it behind A. So behind A, we have 4, 5, and 6. We could imagine, here's a good plane. Choose a front there. And then, where are we? A, B, C, D. So behind A, we have D, and then in front of D, we have 2 objects, 5 and 6, so these need to be split. This is plane E. So in front of we have E, and E has 5, which has 6, and then 4. Now this is just roughly done. This isn't, I'm going to say there's liable to be some mistakes in here. I'm just trying to illustrate how the idea behind a binary space partitioning. And how you take a plane, you choose a front, you choose a back, and you split it. So you do this until there's only one object in each remaining zone, and you can see here that we've done that. And it can be a little hard to visualize because, like, I'm going to circle it over here. Like, unless you know the structure of the tree, why is 3 not related to C? Because 3 is at a higher level, right? 3 is behind B. Once we're lower, we forget that C only looks at 1 and 2. So it can be a little bit hard to visualize. So this is a binary space tree. This is how it works. And there are a lot of benefits. One is the traversal algorithm is linear time. Okay, linear to planes, so we can go through very, very quickly. And the planes, they have this forward and back. So it turns out that if you build and traverse in a strict order, so if you build it with a certain order in mind and you traverse it with the same strict order, you can guarantee ordering of the objects that you hit first. You go in front, you go in front, you go in front, you go in front, or you're going back, you go back, you go back, you go back. You're going to get the object to the back the first. So you can guarantee back to front order. Which is really nice. It also forces splitting of any intertwined objects. Remember that problem we had earlier? I'm going to write that out again. That's really messy. So remember that example we had earlier? I'll draw it out again. This one here. Well, the binary space partition will keep splitting and making new geometry. Yeah, it's red and green. Sorry about that, everybody. Let's not use red and green. Let's use blue. In this case here, we have intertwined geometry. Well, the binary space partition won't put up with that. It'll split it and split and split until we break it up in some kind of way, maybe like this way, where you don't have that intertwined nature before, and then it'll split it up in the middle. So it'll actually break it down. So it forces splitting of these intertwined objects, which cause problems for us. So if we can guarantee forward to back traversal, or back to front traversal, and if you can force split these intertwining objects, then we come back to an oldie. The painter's algorithm works. So if you use a BSP, a binary space partitioning tree appropriately, we do not need a Z buffer. So if memory is short, although you have the tree, you don't need to do that, and it's actually a little faster. Okay, so especially in the 90s and early 2000s, those were really big benefits when games still couldn't rely on good hardware and that kind of thing. Okay. Now, they're not all good. There are some problems with BSPs. Okay. One is you end up splitting a lot of geometry. You end up splitting a lot of geometry. And so what happens is this is a large increase in your polygon count. So you lose some of the gains that you had, and you take up more memory because of that, okay? It can also be really hard. It's hard to do a good job of generating this tree, okay? It's hard and it's time consuming to generate a good tree. So it's not a freebie. It's not a gimme. If your solution is simple, maybe you don't want to go for this one because it's a lot of work. It's really complicated, and it's because it's hard to do. Oh, I'm missing one. Where am I? Yeah, it's also hard to add any moving objects. Okay, any new or changing objects. Because of the way the space partitioning works, you add something somewhere, it'll mess everything up. So you use for static scenes. So if you're using it for a video game, you might use this for the city geometry that never ever changes. Anything that changes, people, enemies, moving things, you probably wouldn't use this data structure. You could use something else, but you can still use a BSP for the static stuff. Overall, BSPs are actually still very popular. They're very good. You actually even see them in robotics and collision detection, things like that. And they're good for really dense scenes. Dense and complex scenes. But if it's useful or not and how useful really depends on so many factors, okay, on the application. So you really need to learn more about them if you want to use them properly. In fact, if you're curious, I gotta say I was really surprised. Wikipedia actually has quite a nice primer with pseudocode and everything in there. It's very accessible. So if you're curious about this beyond what we're talking here, check out the Wikipedia page on binary space partitioning. Great. Thank you.